Hello everyone, welcome to Vigyan Bharat. We are back again with another interesting video. In this video today, I'm going to discuss the complete solution of the problem for 14th of July 2022. So let's move ahead with the problem. This was the expression for the result which we were supposed to prove that given any two non-empty subsets A and B with the property that A is contained in B, this one, then we were supposed to prove this result that greatest lower bound of B will always be less than equal to greatest lower bound of A, which will be always less than equal to least upper bound of the set A, and finally it will be less than equal to the least upper bound of the set B. So this inequality is very useful whenever we are studying the concept of least upper bounds, greatest lower bounds. So this inequality will going to help you when you are doing some good problems. So just a quick information that do watch the video till the end for a better clarity, and you can pause the video and read this quotation yourself, quote of the day by some great mathematician John Allen Paulus. So you can read this. And moving ahead with that, this is just again a good information for you that if you're new to our channel, then do join our Telegram group. You can find its link in the description as well as in the about section of the channel. Okay, so let's move ahead with doing the proof of that problem. So in order to prove that problem, I require two notions. Someone who is doing that, they should have a knowledge what is an upper bound and lower bound for any non-empty subset of R. Suppose that non-empty subset is A of the set of real number line. Of course it is non-empty. Then I should know what it means for an upper bound and lower bound of a set A. And second important information that I should know is what I mean for again this non-empty set to be bounded above and bounded below. Okay, let's move ahead. Let me just quickly note down the statement which we're supposed to prove. We are given that let A and B be two non-empty subsets of real line R with the condition that is given that A is a subset of B. Then we have to prove that expression which I just wrote above, greatest lower bound of the set B will always be going to less than equal to the greatest lower bound of the set A. Further, it will going to less than equal to least upper bound of the set A, and it will going to be less than equal to the least upper bound of the set B. So I'm interested to prove this. So as I told you earlier, I should know what it means by an upper bound. So let me quickly define what it means by an upper bound for a non-empty set. Upper bound. It's very easy concept. Some of you might have already know that. So what is the definition for this? Let again assume my standard notation be A, that my A is a non-empty set, some subset of the real line, and there is a scalar which I called alpha, which is again a real number. Then this alpha is set to be, I'm writing directly, this alpha is set to be an upper bound of the set A if this holds. That is, for each x in the set A, this should hold, that x is less than equal to alpha. If such a alpha exists and it satisfies this condition, then in this case, this quantity alpha is called an upper bound. Upper bound of the set A in R. Fine. So now there's a good question that you should ask yourself, that what it is geometrical interpretation. What can I understand by this expression which I've just wrote it above, the definition basically. So what you can interpret geometrical interpretation. I ask you to just once pause the video and try to think it yourself. I hope you have given a pause to it and you have given a thought to it. So let me just quickly tell you what it means basically. Its geometrical interpretation is very simple. This means that the elements of the set A lie on the left of alpha. On the left of alpha. On the real number line. On the real number line. So this is its interpretation. You can easily understand because we are in R right now. Just let me quickly try to let you visualize this, what I mean by that. Just a second. Yeah. Suppose this is my real line. This is my real line. Yeah, now let's look good. And I chose my alpha to lie over it somewhere over here. See, suppose this is the position where my alpha lies, and my elements of the set A lies over somewhere here, either this or this. They may be anywhere, but what I'm interested is these may be my x, which lies on the left. They lie on the left of alpha. This is this way, so it extends till plus infinity, and it in this direction it extends till minus infinity. This is my real line. This is some alpha over here. So in this case, when all the elements of the set, these x are coming from the set A, so in that particular case, such a alpha is said to be an upper bound. Is said to be an upper bound of set A. I hope this is clear to you. And just a quick answer to the second requirement, this one. This I have already defined what is upper bound. Now you can on the similar lines you can easily define what it means by lower bound for any non-empty set. You can easily define yourself. Now let me just go back. So in that case, when such an alpha exists, which we are calling to be the upper bound, then in that case the set A is said to be bounded above. Said to be bounded above. Bounded above by alpha in R again. In terms of quantifiers, that is in language of mathematics, you can easily write that if this A is some non-empty subset of R, then it's said to be bounded above in R if there exists some alpha in R with the property that this should hold for every x coming from set A. Okay, let's continue the proof. So before beginning ahead with the proof, I need just an important result which I'm going to use when I'm going to prove that above expression. So the result is for any non-empty subset A of R, non-empty subset A of R, this should hold greatest lower bound of A is always less than equal to least upper bound of the set A. So this is the result which I'm going to use while proving that. So this holds in general. Now let's go back again to the expression which I'm supposed to prove. Yeah, this one. So just let me quickly crop this from here and bring it to the bottom. Just a second. Much better now. So let me just cut it, or let me just copy it, and let me just paste it again for you here. Perfect. Okay, so now I'm interested to prove this inequality. So whatever I said now, try to listen it very carefully, and if you try to listen it. So I can, in order to prove this, what I can do, I can prove this in two parts. If I am able to prove the first part, that the first inequality, greatest lower bound of the set B is always less than equal to greatest lower bound of the set A, and the second step I am going to prove that the least upper bound of the set A is less than equal to the least upper bound of the set B. In order to prove this, let me call this star. In order to prove star, I will prove 1 and 2 first, and then use this, let me call this A. I will use this A to combine 1 and 2. Okay, so let's go ahead in the proof. Let's first try to prove the first step. Okay, now I'm interested to prove this one. Greatest lower bound of B is always less than equal to the greatest lower bound of the set A. Now, if I want to prove this, if I'm able to show that this quantity is a lower bound, of A, then the proof is straightforward. So what I do now, so let small m I assume to be the greatest lower bound of the set B, where of course this small m is a real number. So because if m is now the greatest lower bound, which I have assumed, so by definition, therefore, by definition of greatest lower bound, we have m is less than equal to x for every x in the set B. This will hold automatically by the definition of greatest lower bound. Okay, so let me call this, suppose, say my equation 1. Okay, now we know that because since A is a subset of B, this information we already have. So because A is a subset of B, equation 1 holds for every element of the set B, so it must, in particular, it should also hold for every element of the set A also, because all the elements of set A lie in the set B, as A is a subset of B. So therefore, we can conclude from one using this information that m is less than equal to x for every x coming from the set A. Now if such thing hold that all the elements of the set A are greater than equal to m, then from here we conclude that this m is a lower bound, for the set A. I ask you to here think what I have just written, very simple, but you have to pause the video and take some time and try to think over it. If this hold, then I am writing it directly that m is a lower bound, so it's by definition it will hold. The result is very, now this is what I have just this result is by definition, okay, that m is a lower bound. Now there is something again which I can conclude more from here, that if m is a lower bound for the set A, then the greatest lower bound, whatever the greatest lower bound of the set A, it will always be going to be greater than equal to a lower bound, which is m. In our case, that is, this I can again write it as m will always be less than equal to the greatest lower bound of the set A. I hope this step is clear to you. You can take a pause and think over it, whatever I have written. So from here we conclude that our m was the greatest lower bound of the set B, now which we have shown is less than equal to the greatest lower bound of the set A. So, and if I use this result now, this result that I know that the greatest lower bound for any non-empty subset A of R is always less than equal to its least upper bound. So directly I can use this, and from here I can write least upper bound of the set A. I can combine these two using that result. Fine. So now let me call this some capital B equation. Now I'm left to prove this one. I have to prove the second step. LUB of A is less than equal to LUB of B. To prove LUB, least upper bound of the set A, is less than equal to the least upper bound of the set B. Let me change color of the pen. Yeah. So in order to show that, what I will try, will show that least upper bound of the set B, that LUB of B, is an upper bound of A, is an upper bound of A. So this I will try to show in order to prove this one. Fine. So again I assume capital MB, the least upper bound of the set B, where again this M is some real number. If capital M is the least upper bound for the set B, then by definition again this implies this X is less than equal to M for every X coming from the set B. Therefore again in particular, because there is a subset of B, so this should also hold again for every element of the set A. The reason is very simple again, because A is subset of B. Now if this holds for every X in A, so from here I can see that this is now an upper bound. What this is now, an upper bound for this set. For the set A, M is an upper bound now. So therefore, if M is an upper bound for the set A, then the least upper bound of the set A will going to be less than equal to an upper bound, that is M in our case. Fine. So now this implies the proof is very simple now. The least upper bound of the set A is less than equal to capital M. I have assumed to be the least upper bound of set B, so I can replace it with this. So let me call this something, say equation C. Now if I combine equation B and equation C, combining equation B and equation C, what I get? Let me just quickly note down equation B for you. GLB of B less than equal to GLB of A less than equal to LUB of A. GLB, greatest lower bound of the set B, less than equal to greatest lower bound of the set A less than equal to the least upper bound of the set A, and this is less than equal to the least upper bound of the set B. So this completes our proof. Now we have completed the proof, but let's verify the result for some particular cases. Let's verify. Let's do an example. Let I choose A to be this open interval, semi-open I would say, open at 0, close at 1, and B to be this one, open at, closed at -2 and open at 2. So again here these both A and B are of course non-empty and subsets of R, and we can make an observation that my A is again a subset of the set B and is contained in set B. So now I ask you to find these 4 quantities yourself quickly. Just try to find these quantity. I ask you to pause the video over here and first find the quantities. Now let me write the answers for you. I hope you have found it yourself. So this is the greatest lower bound of the set B. If you apply the definition, you would find that the greatest lower bound would be -2. Greatest lower bound of the set A would be 0. Least upper bound of set A would be 1, and least upper bound for the set B will be 2. So you can easily verify that this holds. You can substitute the values and check the sign of the inequality. Now just before concluding the video, here is some observation again which you should make, that greatest lower bound of the set B lies in B, whereas greatest lower bound of the set A does not belongs to A. 0 is not a member of A. 1, that is the least upper bound of A, again belong to A. The least upper bound of the set B does not belong to B. So here in general what we observe, that it might happen sometimes that these quantities may lie in the set or may lie outside the set. So this can happen. So I hope you find this video to be useful. If you have any queries anywhere in the proof which I have just completed, if you have any queries anywhere throughout this proof, feel free to drop in the comment, and do like the video, and if you find it useful, and do join this group. It will going to be very helpful for you. And thank you so much for watching, and we'll meet again with a good similar video.